In this lesson, we'll look at some useful properties of the squares of integers. Now, the square of an integer is any integer raised to the power of 2. In other words, the square of an integer. So some examples include 9, 25, 64, 81, and so on. Also note that the squares of integers are also known as perfect squares. Let's take a closer look at some squares of integers. We'll begin with 36. Now 36 is a perfect square since it is equal to 6 squared, which we can rewrite as 6 times 6. From here, let's take one 6 and rewrite it as 2 times 3, and we'll take the other 6 and rewrite it as 2 times 3. We have now written 36 as the product of prime numbers. Notice that in this product we have 2 2's and we have 2 3's. This should make sense because we got 1 2 and 1 3 from each of the 2 6's. Subsequently, if we rewrite the product using exponents, we can see that the powers of 2 and 3 are both equal to 2. Here's another example. 11,025 is a perfect square since it is equal to 105 times 105. If we write both numbers as the product of primes, we can see that the prime factorization of 11,025 has a pair of 3's, a pair of 5's, and a pair of 7's. Since the prime numbers appear in pairs, we can see that when we rewrite the product using exponents, each of the exponents is equal to 2. Now, this isn't to say that when we find the prime factorization of any perfect square, the powers of the primes will always be 2. For example, when we find the prime factorization of 576, the exponents are 6 and 2. So the exponents of the primes are not necessarily 2, however, the exponents will always be even. The exponents will always be even because, as we have seen, the prime numbers always appear in pairs. In this example, we have a pair here, 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 and here. So from this, we can conclude that the prime factorization of any perfect square will always have an even number of each prime. In other words, in the prime factorization of any perfect square, the powers of the primes will always be even. Now we can take this rule and create a second rule that says a perfect square will always have an odd number of positive divisors. For example, notice that these perfect squares all have an odd number of divisors. Here's why. In an earlier lesson, we learned that if we know the prime factorization of n, then the total number of positive divisors of n is equal to the product of each of the exponents once they have been increased by 1. Now, if we take the prime factorization of a perfect square, we know that the powers of the prime numbers will be even. So when we apply the formula to find the number of positive divisors, each of the values in the product will be even. Now, if we add 1 to each of these even numbers, the sum will be odd. So the total number of positive divisors will be the product of a bunch of odd numbers. Now, we happen to have a nice rule that says the product of a bunch of odd numbers will always be odd. So we can conclude that this product will be odd. So as you have seen, a perfect square will always have an odd number of positive divisors. To summarize, the prime factorization of a perfect square will have an even number of each prime, and a perfect square will always have an odd number of positive divisors. In this lesson, we'll learn all about greatest common divisors. To begin, the greatest common divisor is the same as the greatest common factor. So you'll see these two terms used interchangeably. Now, the greatest common divisor is the greatest positive divisor shared by 2 or more numbers. To illustrate this concept, let's find the greatest common divisor of 12 and 30. Well, here are the positive divisors of 12, and here are the positive divisors of 30. Notice that 12 and 30 have several divisors in common. They both share 1 as a common divisor, and they share a common divisor of 2, 3, and 6. Now, of all the divisors they have in common, the greatest is 6. So the greatest common divisor of 12 and 30 is 6. Let's try one more example. To find the greatest common factor of 56 and 70, we'll list the divisors of 56 and the divisors of 70. As you can see, the divisors that they have in common are 1, 2, 7, and 14. So the greatest common factor of 56 and 70 is 14. As you have just seen, one method for finding the greatest common divisor is to list all of the positive divisors and then determine which of the common divisors is the greatest. Now, this method can be somewhat cumbersome when dealing with large numbers. So let's look at another technique for finding the greatest common divisor. To demonstrate this technique, we'll find the greatest common divisor of 56 and 70. Now, to begin, we'll find the prime factorization of 56 and the prime factorization of 70. At this point, we'll find all of the prime factors that they have in common. Now, they both share a 2, so we'll note that. And they also share a 7, so we'll note that. So 56 and 70 share a 2 and a 7 in their prime factorizations. So the greatest common divisor of 56 and 70 will be the product of 2 and 7, which is equal to 14. Let's do one more. Let's find the greatest common divisor of 132, 198, and 330. Now keep in mind that it is very rare to have to find the greatest common divisor of more than 2 numbers. However, the technique for 3 numbers is the same as the technique for 2 numbers. So let's proceed. First, we'll find the prime factorization of each number. Then we'll identify all of the prime factors that all 3 numbers have in common. And finally, the greatest common divisor will be the product of the shared prime factors. So the greatest common divisor of the 3 numbers here is 66. So that's the systematic way to find the greatest common divisor. This technique works for large numbers, and it is also very useful for gaining insight into questions involving greatest common divisors. Now you might be wondering, what happens if you have 2 numbers that do not share any prime factors? For example, let's say you want to find the greatest common divisor of 8 and 15. Using the prime factorization technique, we'll first find the prime factorization of 8 and the prime factorization of 15. Notice that 8 and 15 do not share any prime factors. So what then is the greatest common divisor here? When 2 or more numbers do not have any prime factors in common, the greatest common divisor will equal 1. The reason for this is that although it isn't necessarily apparent here, all positive integers have 1 as a divisor. So if we list the positive divisors of 8 and 15, we can see that both numbers have 1 as a common divisor. So the greatest common divisor of 8 and 15 is 1. Now if you want to become an expert on greatest common divisors, you must develop certain skills. First, you must be able to find greatest common divisors by listing divisors, as we did in the very first example. You should also be good at finding greatest common divisors in your head. For example, what is the greatest common divisor of 10 and 25? In other words, what is the largest divisor that 10 and 25 both have in common? It's 5. What about the greatest common divisor of 18 and 45? Did you get 9? How about 20 and 64? The greatest common divisor here is 4. Another important skill you need is the ability to find the greatest common divisor using the prime factorization technique. And finally, you must be good at selecting pairs of numbers that have a certain greatest common divisor. For example, what are 2 numbers with a greatest common divisor of 2? Now there are a lot of number pairs that meet this condition. Can you think of any? Well, how about 2 and 4? They have a greatest common divisor of 2. Or perhaps we could have chosen 6 and 22. Now what are the 2 smallest positive numbers that have a greatest common divisor of 2? Did you get 2 and 2? Their greatest common divisor is 2. Let's try one more. What are 2 numbers that have a greatest common divisor of 15? Well, how about 15 and 15? Or 15 and 30? or perhaps even 45 and 120. There are many more pairs of numbers that have a greatest common divisor of 15, so see if you can find some more. If you can master all of these skills, you will be well on your way to becoming an expert at greatest common divisors.